Hi everyone, I am Vanessa Godoy, and first of all, I would like to apologize for not being able to be online today. And so I will let my email here, and if you have any questions, you can talk to me whenever you want, okay? And sorry again. And second, of course, I would like to thank the International Association for Mathematical Geoscience for the invitation and also for having awarded me. And to tell you the truth, as I have a background in environmental management and science and not specifically in math, it was quite surprising when I was informed about the award. I mean, that I was a recipient of the Vistelius Award. As you already know, this award is quite heavy. I mean, the list of previous recipients speaks for itself. So me as a woman, as a Latin American, as a researcher, I feel so proud and grateful about that. So thank you so much again. Finally, I have no words to thank the Professor Jaime Gomez Hernandez. Not only because he nominated me, of course, but also for his constant support and trust. Thank you so much, Professor. So now let's start the talk. Today, I'm going to show you some results of the research project entitled Upscaling of Water Flow and Mass Transport in a Tropical Soil. We are going to see some results related to numerical, laboratory, and field studies. I hope you enjoy the talk. And again, if you have any questions, you can email me. So now I'm going to share my presentation with you and turn off the webcam. Thank you so much. As I just said, the title of this presentation is Upscaling of Water Flow and Mass Transport in a Tropical Soil, Numerical, Laboratory, and Field Studies. And well, when I say upscaling of water flow and mass transport, I mean upscaling of the parameters that control groundwater flow, that is hydraulic conductivity, and of the parameters that control mass transport, that is dispersivity and partition coefficient. Of course, there are more parameters related to this process, but in this research, we are interested specifically only in these three parameters. So at this point, it's important to clarify the physical meaning of these three parameters for those who are not familiar with them. So let's start with the hydraulic conductivity that, well, it measures the ability of the material to transmit fluid through pore spaces and also fractures, and that in the presence of an applied hydraulic gradient. And well, in other words, it's the constant of linear proportionality between the flow rate and the hydraulic gradient. This proportionality was verified experimentally, of course, and well, I think this parameter is well known. I mean the physical meaning of this parameter. Well, the next parameter is the dispersivity, that is an empirical property of a porous medium, and it is related to the characteristic dispersion or spread of the medium by relating the components of pore velocity to the dispersion coefficient. In this picture, we can see here that black bar here and here is the contaminant source, and the lines represent the contaminant plume. Here we can see that longitudinal and transversal dispersivity are equal to 0.5 meters, and here are also equal between them and are equal to 100 meters. So here we can see that the greater the dispersivity, the greater the spread of the plume. So I think that with this picture, with this figure, it's possible to see the physical meaning of the dispersivity. And lastly, talking about sorption coefficient or partition coefficient, this parameter measures the amount of chemical substance adsorbed on soil per amount of solution. So here in this chart, S, the letter S is the absorption, and it represents the retention of chemicals from the aqueous phase to the solid phase of the soil. And the C sub E is the liquid phase equilibrium concentration. So the partition coefficient is the linear coefficient that relates sorption to the equilibrium concentration. And well, now it's important to mention that all these parameters can be highly heterogeneous at all scales of measurements. So I would say that heterogeneity is the key word of this research. That's because due to the heterogeneity, we have to face two main issues. The first one is how to do the complete characterization of the heterogeneity, as we always have limited information. And well, the second issue is how to incorporate the scale effect. The first issue can be faced by using geostatistics techniques such as stochastic simulation or Kriging estimation, for example. And talking about the second issue, we know that because of the change in the heterogeneity depending on the sample size, the value obtained with the sample of a specified size, the value of a parameter, will not be the same as the one obtained with a larger or a smaller sample. So this is especially relevant if we consider that information obtained at field or at laboratory scale will be then used as input in a numerical model with cells bigger than the scale of measurement were taken. So these two issues are really relevant, but today in this presentation I'm going to talk about the scale effects. In this research project, of course, we have studied the characterization of the heterogeneity and also the characterization of the uncertainty. But today I'm going to talk specifically of the scale effects. And I would say that to handle the second issue, we have two options. Or the numerical models are made by using elements with the same size of the measurements. That is, of course, impractical and very time-consuming in terms of computational terms. Otherwise, some upscaling rule must be postulated. And we can define upscaling here in red as a process that transfers the information obtained at the fine scale onto the coarse scale to be used in a numerical code. And here in this picture, we can see an example of the upscaling of the hydraulic conductivity. And at the left side, we can see in this field, in the hydraulic conductivity field, we can see a grid built by using elements with the same size of the measurements. Here it's 0.1 meters. And at the right side, we can see that the fine grid is then upscaled to the one where the cells are 10 times bigger, here 1 meter. So we can see here that upscale implies smoothing and loss of heterogeneity, but we can also see the same pattern of spatial variability, and that is really important here. And we can also remember that the objective of the upscaling is not, just to perform upscaling itself. We need to obtain a reproduction at the coarse scale of the flow or transport obtained at the fine scale. So if you are studying the groundwater flow, we have to obtain at the coarse scale the same or the similar results of hydraulic heads, or discharge or flux as obtained at the fine scale, right? So in this research project, we have studied numerically and experimentally the scale effect on both hydraulic conductivity and solute transport parameters by using real data from a tropical soil. Of course, we used a tropical soil because it's a soil spread around the roads, really important soil, well, mainly in South America and Africa. And the soil has very peculiar behaviors in terms of soil mechanics. So as I was working in a department of geotechnical engineering, the soil was quite relevant. So now I'm going to show you some results of this research, and this indication of the study area that is located in São Carlos City in Brazil. The yellow dot here is showing where is the location of the city. And we have sampled 45 small scale samples. Small scale, it means 0.1 centimeter of height and 0.15 centimeters of diameter, and also 25 large scale samples with a range of heights and diameters. And we considered a 3D configuration. We also sampled disturbed samples and performed 7 double ring infiltrometer and 5 infiltration in rectangular ditches. Here we can see the sampling of small and large scale undisturbed samples at the field. And here in this picture we can see an infiltration in rectangular ditches of different size where we use to determine the hydraulic conductivity. It's in the field we have not performed transport experiments, only hydraulic ones because of the bureaucratic issues. In this picture we can see the laboratory configuration that we have used. In this laboratory, we performed water flow to obtain the hydraulic conductivity and also solute transport to obtain the observed breakthrough curves. And each one of these letters here are indicating a different size, or better, a different volume of sample used to determine the hydraulic conductivity and the breakthrough curve in the laboratory. Now I'm going to show you some experimental evidence of the scale effect. And here we can see the variation of the hydraulic conductivity in the y-axis with the sample volume in the x-axis. These are the results obtained in the laboratory, and these one were obtained in the field. We can see that for all the exterior volumes, the hydraulic conductivity increases with the sample volume regardless the method used. That is very interesting actually, because for the first time this kind of research was reported for the studied soil, and also from these results we can agree, of course, with the limitations here in the volume we have, that there is no a sample volume where no more variation on the hydraulic conductivity were observed. And again, considering that we have a maximum volume, studied volume of 3 cubic meters. These results are part of the results published in these 2 articles and those 2 papers. So if you want to see more details about this research, you can look for these 2 publications. And well, continuing to show experimental evidence of the scale effects, in these pictures are shown the variation of the dispersivity of the potassium and the chloride with the sample height. So we can see that the behavior is clearly exponential if, for potassium and also for chloride. That's a very interesting result again, since many papers have been published trying to determine the relation of the dispersivity with the scale, and many of them recognize that the relation is not linear, and we are here proving experimentally that this relation is not linear for the Vistelius soil here and also for these conditions. However, we also know that mostly in the daily practice of the modeler of the, mainly when we are working with transport, a linear relation where the dispersivity is equal to 10% of the dimension is still used in the daily practice. No. And well, here in these pictures, we can see the variation of the partition coefficient of the potassium and chloride with the sample volume obtained also experimentally. The partition coefficient of the potassium and also the chloride tend to increase with the volume following linear relation, and this is clearly this can be clearly seen for the potassium, and maybe not too good for the chloride, but in general you can say that this is that's following a linear relationship. And well, I would say that the clear or almost clear dependence on sample volume can be explained for the large number of absorption sites as the volume increases, together with the large heterogeneity of those sites. So if you have a large sample with sample volume, so we will have more absorption sites in this sample. So the relation, a linear relation can be expected in this situation. We have also performed numerical upscaling based on real data from laboratory. In this case, we have used two methods. The first one is a simple average by using a p-norm, and the second one is the Laplace with skin method. In the Laplace with skin method, and as we see here in this picture, the flow problem is solved for each block or cell for a variety of boundary conditions, resulting in the best equivalent K, or hydraulic conductivity. So here we can see the solution of the flow for a range of boundary conditions indicated by these black arrows. In this picture, we can see the comparison between the average flux obtained for each one of the 70 realizations at the fine scale and different block size at the coarse scale using the p-norm with a p exponent equal -1, that is the harmonic mean. And here in the y-axis we can see the result at the coarse scale, and at the x-axis we can see the result at the fine scale. So we see here a comparison. And well, it's noticeable that for grids bigger than 0.5 meters, so here, so 0.2 meters, 0.4 meters, 0.5 meters, thus to remember that at the fine scale our grid have 0.1 meter. And so for grids bigger than this one, that's 0.5 meter, the upscaling method did not reproduce very well at the coarse scale the flow obtained at the fine scale. And also we can see that the errors increases with the increase in the block size as expected, because of the loss of the loss of heterogeneity at the small scale. In this picture we can see the comparison again between the flux obtained at the fine at scale and different block size at the coarse scale, but in this case the results were obtained by using Laplace with skin method. It's again notable that the upscaling method reproduced in this case very well at the coarse scale the flow obtained at the fine scale. The error again increases with the increase in the block size, and only the block size equal to 12 meters. I mean, this results in a large error, which can be attributed to, I would say that a large size of the block regarding the correlation length, that in this case is 4 meters obtained by the variography. We also can see here that the reduction in the number of elements was very impressive. Actually, we started in the fine scale here by using 384,000 elements, and then using only 6 or even 1 resulted in a good reproduction of the flow at the fine scale. So this result is really interesting in terms of computational costs. Here we can see the qualitative result of the upscaling by using the Laplace with skin method. Again, we can clearly see that there is a smoothing and a loss of heterogeneity, but we can see the same pattern of spatial variability in the coarse scale and in the fine scale, and that is what we are looking for with the upscaling process. And well, just to conclude, I would say that with this research project, we saw experimental evidence of scale effect in water flow and mass transport for a tropical soil. We also saw that laboratory analyses have corroborated some theoretical upscaling results. And finally, we saw that simple averaging methods cannot be enough to correctly upscale water flow. And also, it's the same for transport parameters. I did not show you the results for simple averaging to upscaling transport parameters, but I can say that the result is the same. So that's it. Thank you so much for your attention. As I said before, if you have any questions about my talk, you can email me whenever you want. So thank you again, and bye bye.